Okay, we want to run an Anova here with our outcome being the win margin. In other words, how much does a player win by? Just take a real quick look there. The first row, 357 versus 302. So player 1 here won by 55 points, 357 minus 302. So that win margin, how much the winner wins by, is what we're interested in analyzing, and we want to see how much that corresponds with the number of blanks, these wild tiles that can be used as any letters. In order to do that, let's first take a peek at some visuals, and we'll go to descriptives. So we want to know about the win margin, pop that in, and we want to split it by the number of blanks. That'll create our different groups, and that already gives us the averages. So right away we can see that the average win margin of the group when you had 2 blanks is higher than these other two. What we don't know yet is if this is a significant difference, or if there's any significant differences at all between these three numbers. We can also see that the standard deviation within those 3 groups are roughly the same. So that can tell us that we meet that homogeneity of variances assumption. Standard deviation is just the square root of variances. So whether the standard deviations are the same or the variances are the same is the essentially the same question. So we do see that those are relatively equal, although there will be a chance in the test to run a more sophisticated objective test on whether or not these are relatively equal. We can also go to the plots here and take a look at distribution plots. This doesn't really help us too much, although we can check whether or not it's normally distributed within each group here. More importantly, let's grab the box plots for the 3 groups. So whether we're looking at these histograms or more commonly we just look at them all on a single chart, we're looking for any severe skews, and we see maybe an outlier or 2 here, but nothing really that gives us cause for concern. Plus, this particular assumption of normality, Anova is robust to this assumption, which means if it's not really normal, it's not going to impact the results too much. So certainly what we see here looks fine for normality, and again, like we said, the variance we met already. We can also take a look at the QQ plots, but I'm going to do that when we actually run the Anova. So I'm going to go ahead and run the Anova. Again, win margin is our dependent, and blanks number is our factor. And we don't need this. Let's see. Here's the actual homogeneity test, and I'm just going to get a QQ plot of the residuals, the standardized residuals here. So there's that normality of the residuals, pretty good, coming up a little bit on the tails, but again, certainly within what we're looking for. Here's that test for equality of variances. Here is a rare case. When you're doing the assumptions of a test, you're actually hoping to fail to reject. The null hypothesis is that the variances are all equal. If you would reject, if you would get a low p-value, that would mean that the variances are quite likely not equal, in which case you'd have to run a slightly different correction factor or test. So here we're well above 0.05, so we don't have real cause to believe that the variances are not equal. So we're going to say we meet that assumption. As for the other assumptions, we can't really check them with visuals. It's more in the design of the experiment. So we're going to, for this case, trust that those worked out. In terms of analyzing the ANOVA itself, we can start off here and see that this is a very low number, much below 0.05. So we can be fairly certain that there is a difference somewhere in the categories of how many blanks people had in the starting position versus how much the winning margin was, how much they won by. And I think that's really all the question asks you to explain. You can see that this is our model or our regression sum of squares, and this is much lower than this number, but we're talking about how many per degree of freedom. So once we divide these out, it turns out that the model or the part of the variance that we do understand is much larger than the part of variance we don't understand. And we put that in a ratio and we divide this number by this number to get our F statistic. It's well above whatever the critical F would needed to be in order to get our statistical significance here. And we'll talk about practical significance in the next part of the chapter.